Hey friends, welcome back to the channel. This is Ahili Bhattacharya, your stats buddy, and today we are going to study the properties of standard deviation. Okay, so let's get started. You think standard deviation is just that scary formula at the end of your textbook chapter? Think again. It's actually a statistical superhero with some incredible hidden powers. Here, we are cracking open my personal notes to reveal not one, not two, but three fundamental properties of ST. In this video, we will cover the first two mind-blowing properties and we will even discover why ST is actually the champion of all deviation measures. Let's get started. Alright, property number one is the foundation of everything. Let's read it together. Variance is independent of the change of origin but not the scale. Okay, that sounds fancy. Let's translate it from stats geek to English. First, change of origin. This means adding or subtracting a number from every data point. Like everyone in a class gets 10-point bonus, which we represented as x plus or minus a. Okay, so change of scale. This means multiplying or dividing every data point, like converting your height from feet to inches, ax or x by a. The rule says SD has a split personality. It completely ignores the first one but has a massive reaction to the second. Let's prove it. The statement is if y is equal to x plus a, where a is constant, then sigma y square is equal to sigma x square. You see? This is the question. Our notes ask if we add 2 to every one of our 5 observations, what happens to the variance? Okay? See, our observations are x1 plus x1, x2, x3, x4, x5. So the mean will be, the mean formula x1 plus x2 plus x3, which goes until 5 by 5. Okay. So our new data yi is equal to xi plus 2. Now let's find the new mean. So y bar is equal to x1 plus 2, x2 plus 2, x3 plus 2 and goes until x5 plus 2 by 5. So, if we cleverly regroup this, we get all the x's together and all the plus 2's together. There are 5 of them, so that's plus 10 total. So, basically sum of xi plus 10 by 5. Therefore, sum of xi by 5 plus 10 by 5 is equal to x bar plus 2. So, the new mean is just the old mean plus 2. No surprise there, but now the magic trick for the variance. We'll look at the core ingredient, the deviation of a point from the mean yi minus y bar, which is equal to xi plus 2 minus x bar plus 2. So here we get xi minus x bar. As you can see closely, plus 2 and minus 2 gets cancelled completely. So we are just left with xi minus x bar. The distance of each point from the mean hasn't changed at all. So when we square these distances and average them, the variance stays exactly the same. You can see it from here. Alright, so superpower number one is SD is immune to road trips. You can move your data anywhere you want, the spread doesn't change. Now, let's try with change of scale. See, the statement is y is equal to ax plus b, then sigma y square is equal to a square sigma x square. The question is, what if we multiply every data point by 3? We define yi is equal to 3xi. The new mean is straightforward. Y bar is equal to 3x bar. But now look at the deviation. Yi minus y bar is equal to 3 yi minus y bar, this part, is equal to 3xi minus 3x bar, which is basically, if we regroup it, 3 is outside xi minus x bar. Whoa, we can understand that the distance from the mean just got multiplied by 3. That's- I'm sorry. So basically, the spread is stretching. Now for the variance, let's follow the calculation line by line. This is the variance. You know the formula for variance. If we get it, see, sigma y square is equal to 1 by n into summation of yi minus y bar whole square, this part. Therefore, which is again equal to 1 by n summation of 3xi minus x bar whole square. Now we square what's inside the bracket, remember, and we get this 1 by n summation n 9 into xi minus x bar whole square. which is basically here. See, 1 by n is a constant, 9 is a constant, so we take that out and we have left summation xi minus x bar whole square. So, what is this? This part inside this bracket, that's the original variance, sigma x square. So, finally, we get 9 into sigma x square. The variance is multiplied by 9, which is 3 square. If you multiply your data by a, the variance gets multiplied by a square. So, we get here superpower number 2. SD is super sensitive to growth rates. Stretch your data and the variance explodes by the square of the factor. See, property number 2. This is a different kind of beautiful. It's beauty contest for averages. The sum of squares of the deviations is minimum when taken about the mean. Alright, in other words, if you had to pick one number to represent your whole dataset and you measured your total wrongness by the sum of squared errors, the mean is the number that makes you the least wrong. It's the ultimate compromise. Let's look at the proof. We want to show that summation of xi minus a whole square is smallest when a is equal to x bar. Okay, so the secret weapon is the clever rewrite. Xi minus a can be written as xi minus x bar plus x bar minus a. We are splitting the total distance into two parts, the distance from the data to the mean plus the distance from the mean to our point A. Now see, we are taking the summation of xi minus a whole square and this part, and we are squaring it. When we square it, we take the formula a plus b whole square, which is equal to a square plus b square plus 2ab. You see this part. See this part, xi minus x bar whole square, we take the summation, which is nothing but actually 0. We will prove it later on. This is actually the property of mean, right? But if you do not understand it from here, I will explain it later. So this one x bar minus a whole square, this is a constant value. If we take the summation of it, then we actually take one I running from 1 to n, right? So we take n outside x bar minus a. Basically, if you see, let's take an example. If you have number 2, see, if you need 2 to be, we get the summation from I running from 1 to 5. So what do? You do 2 plus 2 plus 2 plus 2, like this till 5, which is basically nothing but 2 into 5, which is 10. All right. The same example we took here, 2 into 5, which is 10. Here, we multiply the n. We multiply the number. Okay. Let's erase this part or else you'll get confused when you get the notes. All right. Yes. So now, and the next part, 2xi minus x bar. This xi minus x bar, we need to do the summation. But x bar minus a and 2 both are constants. So we take it out. Now, as I promised that xi minus x bar summation will be 0, how do you prove it? Let me see. How can you prove it? See, not let we. Let's say we have n observations, x1, x2, which goes on till xn. Wait a minute, goes on till xn. The mean is x bar is equal to x1 plus x2 plus goes on till xn by n. Alright, now let's calculate the sum of deviations from the mean, which is nothing but xi minus x bar, which is equal to x1 minus x bar plus x2 minus x bar, which goes on till xn minus x bar. Alright, let's expand this, which is equal to x1 plus x2, which goes on till xn minus x bar minus goes on till minus x bar. Like we have one x bar for each of the n data points, right? So remember how we defined mean, right? See, we can write this one like x1 plus x2, which goes on till xn plus xn minus n into x bar. All right. So if you remember how we define mean, we define mean by x1 plus x2 goes on till xn by n. So if you put it here, divided by n, summation of I running from 1 to n, and then divide by n, and we cancel it out here. So what do we get? We get it 0, right? So this is the proof for this part, why this is 0. And when this becomes 0, when the constant is multiplied to 0, this will be again 0. So what do we get here? Our final conclusion, our final line, which is this: summation of xi minus x bar whole square plus n into x bar minus a whole square. See, this is already 0, right? So both the terms on right are positive as they contain squares. We have to choose the value of a here, for which the RHS becomes minimum. Okay, this can be obtained only when n into x bar minus a whole square is equal to 0, and therefore we prove that x bar should be a. See, this leads us to the epic conclusion written in my notes. SD is the minimum root mean squared deviation. Let's decode this masterpiece. What is deviation? Deviation is xi minus a. What is the square of the deviation? Xi minus a whole square. Now, if we take the mean of it, what is the mean? Summation of xi minus a whole square divided by n. Now, if we take the root of it, see, root is root over 1 by n into summation of xi minus a whole square. This is the root mean square deviation from any point A. And what is the minimum? It's the smallest possible value this can have. We just prove that this expression is minimized when A is equal to x bar, right? You see this one? This is the minimum. So, standard deviation, see, this is basically the exact definition of standard deviation, okay? So, standard deviation isn't just a measure of spread, it's the smallest possible root mean squares measure of spread. It's the optimal, most efficient way to quantify variability. How cool is that? So, yes, there you have it, two of standard deviation's three secret powers. See, first is its chill attitude towards moving data and its dramatic reaction to scaling it. Second, its secret identity as the minimum possible root mean square deviation. But the story isn't over. The third property, how to combine standard deviation from different groups, is a game changer for real world data analysis, and it deserves its own video. If you enjoyed this deep dive and want to see part 2, do me a huge favor and smash that like button. Let me know in the comments which of these two properties surprised you the most. Subscribe so you don't miss the next chapter. Thanks for watching, and remember, stats is for more fun when you look for the secrets. Okay? So stay curious. Bye bye. Take care of yourself.